Welcome to the ePathshala lecture series in computer science. We are discussing about the course computer architecture. This module is about dynamic branch prediction. So, the objectives of this module, we are going to discuss how control hazards are handled in the MIPS architecture. We are also going to look at more realistic branch predictors. So, the previous module we looked at static prediction. So, this module we are going to concentrate more on realistic branch predictors, namely dynamic branch predictors and variations of these predictors. So, if you look at the MIPS branch prediction, longer pipelines, in the case of MIPS, it is a short pipeline where you have a 5-stage pipeline and you have the option of resolving the branch in the second clock cycle itself, which we pointed out in the earlier module. So, if you resolve the branch, that is find out the condition as well as evaluate the branch target address in the second clock cycle itself, you are paying only one clock cycle penalty. So, that is what happens in the case of a MIPS architecture, which is a more aggressive implementation. But you can't afford to do this in a longer pipeline. So, in a longer pipeline, you can't readily determine the branch outcome earlier. And because of this, the stall penalty becomes very, very high, which is unacceptable. In the case of the MIPS pipeline, you can predict the branches are not taken and you fetch instruction after the branch without any delay. So, if you look at MIPS assuming that the branches are predicted not to be taken, then you know you only have to fetch from the sequential path. PC plus 4 is already known. When you fetch your instruction itself, you can always update your PC with PC plus 4. So, the first diagram shows you if the condition is satisfied, if the prediction is correct, then you do not have to pay any penalty. So, the prediction is correct. The second one shows that if the prediction is incorrect, then a bubble has been shown. So, that is the penalty that you have to pay if your prediction is incorrect. Now, this is a view of your branch hazards. So, if you assume that the branch outcome is resolved or branches are resolved in the memory stage, that is the execution stage, you find out the condition and you identify the branch target address, add the branch target address into your PC plus 4. So, the branch outcome is resolved only during the 4th clock cycle, which is your memory stage. So, till then whatever instructions you have fetched, you can see the instructions there. So, those instructions, all the instructions that have been fetched will have to be flushed. So, that is the problem with your branch hazards. Now, if you have to reduce this branch delay, you know that this has to be resolving your branch can't happen in the 4th clock cycle, causing a penalty of 3 clock cycles. You will have to move it to an earlier stage. So, if you move it to an earlier stage, then you know that your branch penalties can be reduced. So, if there is a branch taken, then you know that you can always find out the target address is known by then. So, you have to pay a penalty of only 1 clock cycle. So, that is what has been indicated in these diagrams. But because doing an aggressive implementation like this, that is aggressive implementation, what we mean here is shifting the branch resolution from the 4th clock cycle and the 3rd clock cycle to an earlier stage, which is the 2nd clock cycle. Now, doing this may give rise to other problems. It may give rise to what are called data hazards. So, if your comparison register, you know, as far as the MIPS is concerned, you only compare two registers and check whether they have the same value or check whether a register contains a value of 0. Now, if this comparison register is a destination of the second instruction or the third preceding ALU instruction, you have a problem. So, that has been indicated here. So, you have an add instruction which modifies R1, you have another add instruction which again modifies that, and the branch or equal to instruction is dependent on your R1 and R4. Now, in this case what happens is, if the branch is going to be resolved in the second clock cycle, by then the data will not be available from the other instructions. If it is a previous instruction, you definitely have a problem, but if it is a second instruction, see, this is where you can get the data. The second preceding instruction has already moved on to the execution stage, so it will be available in that buffer, and the earlier instruction has already moved on to the memory stage and you can get it from there. So, if you have the second preceding instruction or a third preceding instruction which is dependent on the branch, then you can always fetch them provided there is support for forwarding. If there is no support for forwarding, then you have a data hazard coming into picture. So, because of this aggressive implementation, we have landed up with a data hazard. So, you will have to decide which one is better and accordingly do. Now, if the comparison register is a destination of the preceding ALU instruction, then you definitely cannot avoid this even with forwarding. You will definitely have to have one stall. And similarly, if you have a load instruction, because you know the load instruction, the data does not arrive at the execution stage. Execution stage, you only have the calculation of the effective address, and only during the memory access cycle you have the data actually coming to the processor. So, even forwarding can take place only after that. So, if it is a load instruction or if it is an immediately preceding ALU instruction, then you definitely have to stall. And if the load instruction becomes a previous, just the previous instruction, preceding instruction, then things become worse. You need to have two stalls. So, all these you will have to remember that these are examples of data hazards that come up in your MIPS pipeline because of doing a aggressive implementation of moving the branch resolution from the third and fourth clock cycles to your second clock cycle. So, this is again an example of that. So, if you have a load instruction, the load anyway gets resolved, the data comes to the processor only during the fourth clock cycle. So, you anyway have to generate two stalls. Two stalls will have to be introduced, only then the data for your ID stage for the branch instruction arrives. So, that is how MIPS handles your branch hazards. Now, we look at more generic issues with respect to branches. We have already pointed out that branch prediction is a very effective way of handling branches. The previous module we only looked at static prediction. Now, we are going to concentrate on dynamic prediction. So, branch prediction, as already pointed out, is the ability to make an educated guess about the way in which a branch will go, whether the branch is going to take or the branch is not going to take. So, if you look at dynamic branch prediction as against static branch prediction, you have hardware. It is a hardware technique which is used to do the prediction about branches. The hardware records the recent history of every branch, and based on that it is going to make a prediction about the branch. And the basic idea here is it assumes that the future behavior of branches will also continue with the trend. If the trend does not continue and if you have gone wrong with the prediction, then you will have to stall the pipeline while refetching and also update your branch history, so that the next time you will get the proper information from the branch. And because the branch behavior is going to be dynamically altered depending on the actual behavior of the branch prediction is going to be dynamically altered. It is called a dynamic branch prediction technique. Now, if you look at the comparison between your static prediction techniques that we already discussed and the dynamic branch prediction techniques, static prediction basically looking at a static prediction technique of predict taken or predict not taken approach, or it uses the technique of delayed branching, which is much more effective, and it does not make use of any information on real time. At runtime, what happens to the branch, you are not going to really look at that and keep modifying your prediction. It is a static prediction. It does not make use of any hardware there, and it is not really it is easier to implement, and it may be a simple method for single issue processors, but it may not be very effective for multiple issue processors because branches become more frequent and you may have to resolve them much more effectively. And there is no hardware support here. So, if you have to make use of it appropriately, then you will have to think of some hardware support for better prediction. Now, if you look at dynamic prediction, there are different techniques that are available for dynamic prediction. All of them make use of history based prediction. So, you have what is called a branch prediction buffer which is available, which stores the earlier prediction, and based on that you get the prediction about the subsequent execution of that branch. And if you go wrong, you can always keep changing the prediction. So, that is why it is called dynamic prediction. So, it uses information on the real time behavior, runtime behavior of the program, and it obviously gives more importance for multiple issue processors, because multiple issue processors you have multiple branches coming into picture and predictions become more critical and more important as you go on to multiple issue processors. And obviously, compared to static prediction, dynamic prediction has an improved accuracy of prediction. So, as I pointed out earlier, when you look at an n issue processor or a multiple issue processor when compared to a single issue processor, when you issue multiple instructions every clock cycle, obviously more of them may be, you may come across more number of branches. So, branches will arrive up to n times faster, and recall Amdahl's law, you know that the relative impact of the control stalls will be larger with a lower potential CPI. And with speculation, it is all the more so, where speculation allows execution past branch and then discard it if the branch fails. So, you have even started executing the instruction when you go in for a speculative execution. You just do not stop with just fetching and decoding the instruction, you go ahead and even execute the instructions. So, when you have started executing the instructions, you have done such a lot of work and then find that the branch prediction fails, you have a lot of penalty to pay. So, you have a very great performance loss. So, you will have to be very, very careful about dynamic prediction. The prediction accuracy should be really high for a dynamic branch predictor to be very effective. So, the key concept behind dynamic branch prediction is you make use of a hardware which looks for clues based on the instructions, or it can use past history. So, you maintain a history table or a branch prediction buffer which contains information about what a branch did the last time or the last few times it was executed. So, a function, the branch prediction, the dynamic branch predictor, obviously the performance of that depends upon the accuracy of your prediction and the cost of misprediction. That is the penalty that you will have to pay if at all there is a misprediction happening. So, there are basically 7 branch prediction schemes that we look at: a 1-bit branch prediction buffer, a 2-bit branch prediction buffer, a correlating branch prediction buffer, a tournament branch predictor, a branch target buffer, and a return address predictor, and finally an integrated instruction fetch unit. Some of these were already pointed out in the earlier module. We just discussed about a branch target buffer which is used for a speculative execution, and a return address predictor which is used for predicting the return address. We will get into details of this as we proceed. So, the first one is a 1-bit dynamic branch predictor. So, in the case of a 1-bit dynamic branch predictor, we make use of a branch history table or a branch prediction buffer. This hardware is common to all the dynamic branch prediction schemes. And what you do here is, why it is called a 1-bit dynamic branch predictor is, every one of these addresses, suppose if you have a 1K branch predictor, then it means that you are going to store 1024 entries or 1024 branches information. And each of these entries has only one bit, a 1 or a 0, indicating whether the branch is predicted to be taken or not. A 1 probably indicates that the branch is predicted to be taken, a 0 indicates that the branch is predicted not to be taken. So, what the 1024 here means is, that is the address bits. So, you are trying to associate the address of a branch to identify a branch, and you are going to store information as to whether the branch is predicted to be taken or not. When you are storing the address of a branch, obviously it is not possible to store the entire branch address. Then you can imagine the size of your branch history table, it is definitely not possible. It is going to be the size of your main memory, that is not possible. So, we are going to compromise and store only a few entries as your branch history table. What you are trying to do there is, you are going to use only the lower, some of the least significant bits of the PC address to index into this. So, as I mentioned, suppose if you are looking at a 1K prediction buffer, then I have 1024 entries and the address bits are going to be 10 bits. Your actual address, PC address, may be a 32-bit address or a 64-bit address, but I am using only the least significant 10 bits. So, when you are using the least significant 10 bits, it is enough if I maintain a 1K buffer. Each one of them is going to have a 1-bit entry. Now, the downside of this is that many of the branches may have the same least significant 10 bits. So, you may after all get the prediction of some other branch, but that is okay. That is okay in the sense that many a times we do not write, the basic block of your program is not too large. So, the addresses may not change too much with respect to, even if you look at a 10-bit address, it does not change beyond 10 bits if you are looking at short bodies of your program. So, it is very effective. So, that is the idea of a 1-bit dynamic branch predictor. So, when you get a branch, what you do is use the least significant bits, index into this branch prediction buffer, get the prediction from there. So, if the predictor says that the branch is predicted to be taken, then assume that the branch is going to be taken and fetch from the target address. If the predictor says stores a 0 and says that the branch is predicted not to be taken, then bring it from the not taken path, that is a sequential address. So, that is how a dynamic branch predictor works. Now, this is a prediction. So, you assume that the branch target address is known to you, you assume that the sequential address is known, accordingly fetch. Now, when you actually resolve the branch and find out that your prediction was wrong, you do not have to pay any penalty at all. But if you find that your prediction was wrong, you fetch from the wrong path, then of course you will have to flush your pipeline, then you will have to bring in from the correct address and at the same time update your branch prediction buffer. So, the branch prediction buffer earlier pointed to a wrong prediction. So, a 1-bit dynamic branch predictor, every time you do a misprediction, you are going to change the prediction so that the next time it is going to give you the next other prediction. It flips. So, that is what happens in the case of your dynamic branch prediction. The shortcomings of your dynamic branch predictor is that, suppose if you have an inner loop like this and an outer loop, the mispredict is taken as the last iteration of the inner loop, because inner loop, say for example, is going to execute 100 times. So, the first time you make a misprediction, probably it gets set as taken. So, 100 times you keep executing the loop. So, the last iteration of the inner loop also, it will assume that the branch is going to be taken, whereas the branch is not going to be taken, it is going to go to the outer loop. So, that is going to be a misprediction. Now, again from the outer loop, when you are going to move to the inner loop, it is still predict that the branch is not going to be taken, because you would have changed the bit, but it will actually take. So, that is the shortcoming associated with your 1-bit predictor. So, for example, consider a case where you have a loop instruction which executes 9 times in a row and then does not take once, the last time it comes out. Now, in this case you have two mispredictions. Whatever you assume, initially let us assume that the branch is predicted not to be taken. So, the first time you enter the loop, that is going to be a misprediction, it will immediately be changed to taken. You executed 9 times, it will be correct. The last time also, the last iteration also, it will predict it to be taken, but you are going to exit the loop, that is the first the next misprediction you come across. The second time you enter the loop, it will still predict it as not taken, because your last iteration was not taken, but you will find that the branch is taken. So, even in clear cut loops like this, clearly defined loops like that, where 90% of the time the branch is going to be taken and only 10% the branch is not going to be taken, you will find that you will have two mispredictions and it is only 80% correct. So, that is the shortcoming with your 2-bit predictor. So, in order to avoid the problem associated with your 1-bit predictor, people came up with what is called the 2-bit predictor. So, the only change, it is again a dynamic branch predictor. So, the only change that occurs here is, otherwise conceptually it is the same. You are going to have a branch history table. The history table is going to be indexed by a few of the least significant bits of your branch address. All that is going to be the same. The only thing is the prediction information is stored as a 2-bit information. Earlier we just stored it as a 1-bit information, and every time you did a misprediction, you flip the bits from 1 to 0 or 0 to 1. Here it is not like that. You have a 2-bit information maintained, and the predictor itself is maintained as a 2-bit 4-state diagram. So, this is a 4-state machine that is shown. So, you try to do change in prediction only when you do 2 successive mispredictions. So, assume that you are in the predict taken state, which is the first block on your top right. So, you are in the predict taken state. So, if your prediction is taken and the actual outcome of the branch is also taken, you are very correct, you just continue to remain there. On the other hand, if your prediction is taken and the branch is actually not taken, you mispredicted it for the first time. So, when you mispredict for the first time, you do not immediately change your prediction, but you move on from that first state of dark blue to the next state of light blue, where I am still giving an outcome of predict taken, but I am not very sure this time. You can also call it a strongly taken state and not so strongly taken state. So, I have done a misprediction, I am still predicting that the branch is not going to be taken, but really not very sure. So, you stay in that state. Now the next time the branch outcome is again calculated, and if you find that the branch is actually taking, then you go back to your original stage. It did not take once, but it was okay, you go back to your the first state itself. On the other hand, if you are in the second state and the second outcome is also wrong, the branch you predicted to be taken but the branch is not taken, I have done two consecutive mispredictions. So when you do two successive mispredictions, you move on to the light green shade where you strongly predict that the branch is not going to be taken. So in this state also you follow the same procedure. So as long as you are in the strongly not taken state and the branch is actually not taken, you continue to remain there. The first time you do a misprediction, you move on to the next state, but you are not very sure there because you know that you've gone wrong once, but I'm not changing the prediction. I'm not very sure about my outcome, but I'm still trying to maintain the same outcome. When you do two successive mispredictions, then you will have to obviously change your prediction. So that is the basic behind your 2-bit predictor. The main concept here is that a few atypical branches, it is not a typical behavior of a branch. Sometimes the branch behaves differently, and because of that I do not have to change a prediction as you did in the case of a 1-bit predictor. Only if it does the same thing twice in a row, you go ahead and change the prediction. So this is especially useful when multiple branches share the same counter. Because you make use of the same least significant bits, you may have multiple branches sharing the same counter value because they make point to the same least significant bits, and because of that you may get different outcomes for different branches. So it does not really make sense to immediately shift your prediction whenever you go wrong once. So you wait for 2 times and then make a change in prediction. Now the same concept of a 2-bit predictor can be extended to n bits. So suppose for example you are looking at n is equal to 3, then you have 8 states, out of which 4 of them will be treated as a not taken approach, not taken state, and 4 of them will be treated as taken state, and only when you do 3 successive mispredictions you will switch between states. So people have examined with the 2-bit predictor, 3-bit predictor and all that, and they have proven that a 2-bit predictor itself is good enough for dynamic branch prediction. So you do not have to really extend it beyond a 2-bit predictor. So the accuracy of predictor, the misprediction basically happens because of the wrong guess for the branch, or you got the branch history of the wrong branch. You did not, when you index it, you got the branch information about a different branch. So these are some examples to show how a 4K entry, what is the performance associated with your 4K entry. Now your 1-bit predictor, 2-bit predictor, all of them point to branch prediction based on the behavior of a particular branch. But in many cases we find that a branch behavior is not only dependent on its own behavior, it depends on the behavior of other branches. So how do you correlate the behavior of one branch with the behavior of other branches? That concept is what is called a correlating branch predictor. Now the correlating branch predictor makes use of what is called a global information. Global information means it is making use of the information about other branches. So you generally talk about an m comma n predictor, which is a correlating predictor, where the predictor maintains global information about m different branches, and each of these branches is implemented as an n-bit predictor. So n will always restrict it to 1 or 2. So each of these individual predictors is implemented as either a single bit predictor or a 2-bit predictor, and m indicates how many global branches history you are maintaining. For example, when I am trying to suppose if m is equal to 2, when I make decision about a particular branch, I am going to look at how the earlier 2 branches got executed, and depending upon their behavior, I will decide about the behavior of this branch. So when you are looking at 2 branches, you know that there are 4 possibilities. Both the branches could have taken, both the branches could not have taken, one taken and not taken. You have all the 4 combinations of 0, 0, 0, 1, 1, 0 and 1, 1. Accordingly, you have 4 different options to choose from, and based on those options you choose the prediction for a particular branch. So basically the idea is, instead of just maintaining a counter for each branch, you try to maintain a counter for each branch and the surrounding pattern. So, if the surrounding pattern belongs to the same branch, then it is called a local predictor. If the surrounding branch includes other branches also, it is called a global predictor. So, this is an example of the third branch being dependent on the earlier two branches. As you can see the code here, the third branch is dependent on the earlier two branches. So, a 2-bit predictor is not going to give you very effective results here. You will have to obviously look at a correlating branch predictor. So, this is the idea of a correlating branch predictor, where I have indicated a 2,2 predictor, which means I am going to maintain information about two global branches, and each of these is maintained as a 2-bit branch predictor. So, and let me assume that I have 4 bits of branch address. So, you have with 4 bits I can have 16 different options. So, I have 16 different addresses. Earlier, in the case of a single bit predictor or a 2-bit predictor, a local predictor, we would have had only 16 different addresses, each pointing to 1 bit of data or 2 bits of data. Now, what happens is you just do not have just 16 predictors. Each of these 16 addresses have 4 different predictors depending upon the 2-bit global information. So, depending on whether both the earlier branches took a 1 1 condition or did not take a 0 0 condition or a 0 1 or 1 0 condition, each one of these predictors will be chosen. So, you maintain information about the earlier branches, look at how the earlier branches behaved. Based on that, you will choose one of these predictors, and each of these predictors will be implemented as a 2-bit predictor. So, that is the idea of a correlating predictor. So, this gives you some performance graphs for indicating the accuracy of the different schemes. One gives you a 4K entry for a 2-bit BHT. The second one gives you unlimited entries for a 2-bit branch history table. The third one, you see that it is only a 1K entry, but it is just a 2,2 global predictor. You find that the misprediction frequencies have obviously come down for all the, it is at least same for some of the cases, but it has come down for most of the benchmark results. So, the next concept that we are going to look at is tournament predictors. Tournament predictors are not conceptually different. So, we have already looked at a local predictor, we have already looked at a global predictor. Tournament predictor, what it does is, it tries to implement multi-level predictors. So, it implements a global predictor, it also implements a local predictor, and it uses a selection mechanism on top of them to decide to choose either the local predictor or the global predictor. So, both these predictors will get implemented, and you have a selection mechanism which will decide to choose either the local predictor or the global predictor. The selection mechanism can again vary. The selection mechanism may say that this time I will choose a local predictor, and once it makes a wrong prediction, I will immediately shift to the other predictor, or only if you do 2 successive mispredictions, I will shift from the local to the global or whatever. So, that is basically what is called tournament predictor, and tournament predictors are basically what get implemented in most of the latest processors, and they are called multi-level branch predictors. So, this gives you some performance metrics about these, performance statistics about these predictors. The percentage of predictions taken from the local predictor when you go in for the tournament prediction scheme, and how the accuracy of branch prediction has varied over a profile based predictor, a 2-bit predictor, and a tournament predictor. So, this again shows you the branch prediction performance. So, now what we have looked at so far is using a branch history table. Now, in all these cases what happens is, we are assuming that the branch history table predicts that the branch is going to be taken. So, unless you know the branch target address, you will not be able to fetch from the target address. So, if you do not know the target address, then this prediction is not going to work. So, as pointed out earlier, it is not just enough if you predict about the condition of the branch, you should also be able to predict about the target address. So, your BTB basically does that. So, in the case of a branch target buffer, what we do is, the branch target buffer stores the target addresses. So, whenever you execute a branch, a conditional branch, you find that the branch is taken, you store it in what is called a BTB. So, the BTB stores the branch target address and the PC value associated with that to identify that it is a branch instruction. You can't just store the least significant bits here. So, the entire PC value indicating that it is a conditional branch that was taken and the associated target address is shown. So, what happens is whenever you have a branch instruction coming in, you do not even know that it is a branch instruction. So, during the fetch phase of the instruction itself, when you make use of the PC value to fetch from the instruction memory, you use the same PC value to index into your branch target buffer. If the PC values match, then this probably is a conditional branch which was taken last time. So, immediately what you do is you take the taken branch from here, address from here and start fetching from there. So, that is what is the idea of a branch target buffer. Suppose if you go wrong, then you know that these instructions will have to be flushed, that entry will have to be removed from the BTB and you will have to pay the penalty for that. So, that is the concept of a branch target buffer. So, the prediction happens after you know that it is a branch and you try to make a prediction of the branch, whereas a BTB is used even before you know that it is a branch. So, that is the idea of a branch target buffer. So, here is an example which shows how you get improvements using a BTB and what is the penalty that you will have to pay with a BTB. Just go through this example. The last one is what is called a return address predictor. As already pointed out, it is not that just loops are going to give rise to branch instructions. Your procedure calls are also going to give rise to branch instructions, and these are much more difficult to handle because function calls can be initiated from different points. So, the return addresses are going to be different. So, normally to handle these return addresses, we maintain a stack data structure and you push the return addresses onto the stack and pop them out on a return. So, that is how a return address predictor works. And last of all, we have what is called an integrated instruction fetch unit. You know that the fetch is becoming more and more complicated because you will have to make a prediction about the branch, you will have to go and fetch the branch in order to the next target instruction in order to avoid the control dependency. So, all this is integrated into a fetch unit. The fetch unit itself becomes complicated where your branch predictor becomes integral part of the fetch unit and you try to do instruction prefetch. You prefetch instructions and you store them in the buffer. All this tries to avoid the problem associated with your control hazards. So, to summarize, we looked at branch predictions, we have looked at how prediction becomes very, very important to handle branch hazards. So, you can't just rely on static prediction, we will have to move on to dynamic branch prediction which are much more effective. And in dynamic branch prediction, we looked at a 1-bit predictor technique and we looked at a 2-bit predictor. Then we moved on to a correlating branch predictors where a branch behavior is predicted based on not only its own behavior, but it is predicted based on the behavior of other correlated branches. Then we looked at a tournament predictor where it makes use of a combination of a global predictor and a local predictor and implements a selection strategy on top of it to select one of these predictors. We looked at a BTB, which is again very effective in handling the control hazards, because even before you know that it is a branch, you access the BTB and get the target address straight away and pay zero penalty if everything goes correct. And we also looked at the importance of a return address stack for prediction of indirect jumps. And last of all, we looked at an integrated instruction fetch unit, which is implemented in most of the processors because fetch itself has become a very complicated process now, which will bring a very important impact on the performance of the processor. So, you try to implement the branch prediction and all that in the instruction fetch unit, do a prefetch of instructions so that you are able to give an uninterrupted flow of instructions to the processor for execution. Thank you.